All right, 4.3, example 5. We're dealing with the fundamental theorem of calculus, which for right now, part 1, what I call part 1, is essentially the shortcut rule for integration. So we're on example 5. It says to find the area of the region. So immediately when you read the word area, you should be thinking what type of number? Positive. Okay, and who's in charge of making it positive? Yeah, we are. Good. Bounded by. So they're going to give you some curves that define like the borders of the region. And you have to essentially identify the country on a map, but you're drawing the map, okay? Find the other region bounded by the graphs of y equals 0. What's another name for y equals 0? The x-axis. Good, good. So there it is. 2 over x minus 1. Well, that's a transformation of 2 over x, or 1 over x. The 2 is going to stretch it vertically. The minus 1 is significant. It moves it down 1, so it has a horizontal asymptote now at -1 and a vertical asymptote still at the y-axis, and it's going to live up here and down here. X equals 1. Okay, well, where's x equals 1 in relation to this x-intercept? This now becomes kind of important when I'm drawing it to scale. Where does that graph cross the x-axis? Well, you could figure it out. Go 2 over x minus 1, set it equal to 0. You get 2 over x equals 1. So x would equal 2. Yeah? So if that's x equals 2, then the line of x equals 1 is going to be in front of it. And the line x equals e is going to be where? To the right of it, yeah? Right here, maybe? So x equals e and x equals 1. Wow, okay. So identifying the region, it looks like it's going to be this little purple nurple region right here and this little purple region. And you notice your x-axis, which I'll draw right here in red because it's kind of important, kind of cuts through the middle. So if I just integrated from 1 to e, is that going to give me the area? Nope. It's going to give me the net accumulation. So I have to set it up on my own. So here we go. Without a calculator, we're in charge. So area is going to equal, when I integrate straight from 1 to 2, since that region's above the x-axis, I should be in good shape. It'll just be 2 over x minus 1 with respect to x. But on the next region, because the y values are below, I'm in charge of making it positive. And remember, we have 2 ways to make that integral positive. What are the 2 ways? We can either put a negative in front, good, and integrate straight from 2 to e. Or we could integrate from e to 2 and put a positive out front. What would you prefer? Yeah, the positive out front, I am actually a bigger advocate of, because when you have 2 terms like that and the second one's negative, there's more burden on you to have parentheses and grouping symbols intact. And if you miss them, you can make a kind of a grave error there. But either way works. It doesn't really matter. Okay, so now we need to integrate it by hand. So the antiderivative is what comes next, and that's kind of the biggest challenge. 2 over x, what's its antiderivative? E to 2. See, I rewrote it and I didn't have my numbers right. Thank you. E to 2, not 2 to e. Nice job. All right, 2 over x becomes natural log of the absolute value of x with a 2 going along for the ride, minus x. Do we need our plus c? No. Plus, it's going to be the same antiderivative, 2 natural log absolute value of x minus x, but now we evaluate it from e to 2. All right, I'm going to work straight down into this region here. I'm going to borrow it, and then we'll maybe shift it around later. Okay, so plugging in the top now, I get 2 natural log of 2 minus 2, and you could drop the absolute values once you plug in, minus parentheses 2 natural log of 1 minus 1. So there's plugging in the top minus plugging in the bottom. Now, because I have a plus sign next, I don't have to really worry about having like some big bracket or something there to group the next ones together. Otherwise, you would. Now it's 2 natural log of 2 minus 2 minus, plugging in an e, 2 natural log of e minus e. And of course, that is a numeric answer. So if this is where you decided to walk away in a free response, I would applaud you for that. But let's keep going and see if we can do anything else with it. Expanding it out, you get 2 natural log of 2 minus 2. What is 2 natural log of 1 equal to? 0, right? Because natural log of 1 is 0. So that becomes minus the negative 1, which becomes plus 1 on that term. And then the green stuff, plus 2 natural log of 2 minus 2 minus, what's 2 natural log of e equal to? 2, because natural log of e is 1. So we get minus 2 and then plus e. So let's see, we got like terms. 2 natural log of 2 plus 2 natural log of 2 makes 4 natural log of 2's. All my constants, let's see, a negative 2 plus 1 is negative 1. Minus 2 is negative 3. Minus 2 is minus 5. And that leaves me plus e. And so there it is. Now, just thinking of what College Board might do, what could they do with 4 natural log of 2? Yeah, they could say it's the natural log of 2 to the 4th, which would be the natural log of 36. Or they might just split the 4 up and call it 2 natural log of 2 squared and make it 2 natural log of 4. Don't bring the whole 4 up there, just bring 2 of the factors up there. Oh, yeah. 4 is the same as 2 times 2 natural log of 2. So let's just bring one of the factors up, and we got 2 times natural log of 2 squared. Yeah, that'd be more like something I think they would do. A little less obvious. Okay, let's see what else they could do, just for kicks and grins at this point. We know what they could do with the natural log that's already there. What if they split the 5 up and called it minus 1 minus 4 plus the e? What could they do here? And we've already had this number appear in this problem, so it's not that big of a deal, but minus the natural log of e minus 4 plus e. And then, of course, if they brought the 4 up, they can have the natural log of 32 minus the natural log of e minus 4 plus e. And then they condense those and call it the natural log of 32 eighths minus 4 plus e. Yeah. Oh, it's 16. Yeah, sorry. I never verified that. My bad. Someone said that, and I just went with it. I'm sorry. Yeah, 16. Yeah. So that would be a great answer choice to bait people. Yeah, 2 to the 4th is 16. Good. 2 to the 5th, 32. Nice. Maybe we were looking at the 5 right there. Okay, anyway, now it says to do it on your calculator. Before we go to the calculator, though, let's go ahead and set it up. You could, of course, do it the exact same way on your calculator. You could go through all this nice work of splitting it up into 2 separate integrals so that it's positive the whole time, and your calculator will give you the right answer without actually saying things. The way we're going to do it, though, is, we're going to integrate straight across from 1 to e. We're going to take the absolute value of the function 2 over x minus 1 with respect to x. And so if we set it up first before we go to the calculator, that's always a good habit to do because you've already thunk out the problem, pre-thunk it out. So math 9 and 1 to e. To get e the number as opposed to e caret open, you can hit second division, or you could say it's e to the first, and then 2 divided by x minus 1. The calculator will read that the right way, and then you hit enter, and you get that. Now let's see if that's equal to the natural log of 16 divided by e. I'll type in a funky version of what we got. Minus 4 plus e. No. I didn't take the absolute value of it. Okay, cool. Case in point, when you have negative values, the integral straight across gives you not the area, but the net accumulation. So this right here is positive, this here is negative, and it turns out, I could tell from my wrong answer by typing it in, that the region above is actually bigger than the region below, right? Because I came out with a net positive. Okay, cool. So let's come back up here and pretend like we did that one on purpose. Math 9, 1 to E. And then how do we get the absolute values? Yeah, math number 1 is a good way, or alpha, I think F2 or 3, somewhere in there. Now let's type it in. Okay, 2 divided by x minus 1. And now are we nervous, or am I nervous before I hit enter? Yes. Yes, I am nervous. I am nervous because I got the 1 outside the parentheses. So let's see if I do a minus 1 inside the absolute values. There we go. Discount double check. How's that look? Before we hit enter, does that look good? Yeah. It is. Now, which one of those is more accurate? Because it's not quite the same. Notice it's the same to 3. It's the same to 4 decimal places, which your calculator is typically right to 3. It's that smart. The bottom one or the top one more accurate? Both? Both are more accurate. Yeah, the top one, because we typed it in as an exact answer. Okay, good. I'm glad we didn't break math. Sometimes we break ourselves, but we fix ourselves as well. Okay, are you getting the hang of it? The difference between area by hand and area on the calculator. Area on the calculator, you take the absolute value of your function first, then you take the integral of it. Make sure you take the absolute value of it when typing it in. It's easy to forget. All right, let's move on to the second part of the theorem very quickly. The second part of the theorem, the fundamental theorem of calculus, that is, deals with the fact, as we mentioned in the beginning, that the derivative and the integral are related how? They're inverses of each other. They undo each other. So what we're going to do first is we're going to define an integral function as a function of x. Okay? That's the first thing we're going to do. So let's say I have this integrand function called f. And we're taking the integral with respect to t. Well, if I then find the net accumulation of that function from some constant a, could be anything in the domain of f, to x, where x is my variable, I'm going to define that to be big F of x. So even though my integrand is a function of t, the integral itself is a function of x, where x is the, in this case, the upper limit to growth. So if you want to think about what that looks like, for instance, let's have a graph that looks like this. And we'll call that f of t, and we'll call that the t-axis, okay? Let's say that my a value is this right here. We're starting here at x equals a. If I want to know what, let's say, big F of b is, well, big F of b now is going to be the integral from a to b of f of t dt. So b might be right here. And so we would define f of t to be the area of that region. And it would be some positive number. Okay? Well, what if I wanted to figure out what the integral was from a to c? Well, that would just be f of c. It would now be the integral from a to c of f of t dt. And c could be maybe somewhere over here. And, of course, that area from a to c now, or the integral in general, I should say, would represent big F of c. I could even pick a value like big F of d, and that would be the integral from a to d of f of t dt. And d might be somewhere over here in negative land. And so I would integrate from a to d. And in this case, that would give me what type of number? A negative number, right? Because I'm going from right to left and it's above. I might even be interested in figuring out what f of a is, right? F of a, plugging it in for x, it would be the integral from a to a of f of t dt. And what would that equal? 0. That would equal 0. So this is a useful thing to define a definite integral as a function of x, where x is the upper limit of integration. Okay? It assumes that you're starting at the same place every time and allows you to compute many different integrals, all based upon the same starting place. Okay? So let's try out example 7 real quick. The graph of f of t is given. Let big F of x equal the integral from 2 to x of f of t dt. Now, by the way, the reason that we change that to some variable that's not x, in this case t and dt, is because I don't want there to be any confusion what the actual independent variable is, right? It's this x, which is that x. It's the upper interval, okay, for the integration. It doesn't have to be t. It could be f of p dp. It could be f of m dm. It just has to be different because if I kept it as f of x dx, now there's too many x's and you're not sure which one actually represents the independent variable. So that's why we change the variable. And t is just another nice independent variable because we're used to it with time. All right, it says use the areas of the regions to evaluate the following function. All right, we want big F of 2. Well, let's see. Let's go ahead and plug it into our function first. Big F of x is the integral from 2 to x. So big F of 2 is going to be the integral from 2 to 2 of f of t dt, which of course we know that's going to be what? 0. Because we haven't accumulated anything because we haven't gone anywhere from 2 to 2. Big F of 9, that's going to be the integral from 2 to 9 of f of t dt. All right, so now we come over here and interpret that. Notice we're starting at 2. So I'm going to go ahead and draw this vertical line here at 2. And we want to go all the way here to 9. Now here's where on a free response you're going to want to indicate your method. Notice that from 2 to 9, I have a trapezoid laying down. Or you can think of it as a rectangle with a triangle, however you want to look at it. I'm just going to look at it as a trapezoid. If you find the area of that trapezoid and you write it real big in the region, you can start using that number in your calculations. All right, so let's go ahead and figure out the area. It's 1/2 the sum of the bases times the height. Well, the height is 20, right? So let's go ahead and multiply that by the half and get it out of the way. It's 10. So it's going to be 10, which is half the height, times the sum of the bases. From 2 to 7 is 5, and from 2 to 9 is 7. 7 plus 5, 12. Times 10, 120. So if you want to actually write that calculation off to the side, that's fine. Once I find the area, I'm going to throw it in there, and I can use that number now. Okay, that happens to be the answer to number 2, because I'm going from left to right. Okay, good. Big F of 15. Well, plugging in first, that's the integral from 2 to 15 of f of t dt. So now we got to go all the way to 15. Well, 15 is over here. I have another little region of another trapezoid down here that I can compute. It's 1/2 the base times, or 1/2 the sum of the bases times the height. The height is 10. And so half of that is 5. And then we'll multiply that by the sum of the bases. From 9 to 15 is 6. And from 10 to 14 is 4. So 6 plus 4 is 10. Times half the height, that's going to be times another 5. 10 times 5 is 50. Oops. Well, the area is 50, and then I can assign it a positive or negative value depending on what I'm doing. So, yeah, now that I have that, I can use those numbers in my calculation. It's 120 minus 50. And if I show that, there's no doubt where we're getting that number from. And now we can compute it, and we get 70. So it's not a real difficult concept. Big F of 18. Okay, that's going to be the integral from 2 to 18 of f of t dt. Now I'm going from 2 all the way to 18, so I got one last little trapezoid down there, and I got to compute its area. And let's see, the height is 10 again, so half of that is 5. The bases are from 6 to 18, which is 2, and 15 to 18, which is 3. 2 plus 3 is 5, times half the height, which is another 5. That gives you 25. And so, what am I going to write for my answer on f of 18? Well, I'm going to just show it all again. 120 minus 50, and now I'm back above going from left to right, so plus 25. So it ends up being your previous answer plus 25, which is 95. And again, those amounts tell you how much you've gained or lost. Finally, the last one here, f of 0. F of 0. Well, that's going to be the integral from 2 to 0 of f of t dt. Coming over here and looking at what that region entails, that's all of this right here, which I can find the area of that. That's a triangle now, and so its area is going to be half the base times the height. The height is 20, half of that is 10, the base is 2, 10 times 2 is 20. So again, I'm writing the area in the region, and now I just have to use that to find the integral. What's the integral then? Negative 20. Good, because we're going from right to left and it's above. So notice it all depends upon that starting value, 2. And then it's the variable x that is the upper interval of integration. And the function could be a function of any variable. We just conveniently choose t because it's not x. That's actually y, okay? You can choose any variable you want. Okay, let's move on to example 8 then, getting closer to what the theorem actually says. It says if big F of x then is the integral from 3 to x of t squared plus t plus 1.
Tables will be set up in front of the Career Center during all lunches so that you can pick up your transcripts. Sophomores, if you would like to receive your transcripts, the sign-up sheets will be available during lunches in front of the Career Center as well, or you can sign up later in the front office to receive yours. Also, if you took the December 2015 EOC retake, please stop by the back office to pick up your scores. Student council members, there will be a meeting today in the Commons area right after school. Attention track athletes, if you are participating in the Cookie Dough fundraiser, please make sure you turn in your forms and money to Coach Starnes by this Wednesday, the 27th.
And teachers, if you could please turn your TVs to Channel 4 for the morning announcements, or you can view them on your iPads at mbhstv.com. Thank you.
Okay, we've already seen graphically why this right here, even though the integrand is a function of t, we've already seen why the integral is a function of x. X is your independent variable. It's your upper interval of integration. We're going to actually show you again down here algebraically or using calculus also why it works. So this big F of x, very similarly, is going to be the net accumulation starting at 3 to some x under the curve of this quadratic, this polynomial. But rather than see it geometrically, we're going to go ahead and simplify it. Okay, I'm just going to keep the left as big F of x. Can I find the antiderivative of that with respect to t? Sure, right? It's 1/3 t cubed plus 1/2 t squared plus t. Do I need my plus c for a definite integral? No. And I know it's a definite integral because I have intervals of integration. They don't even have to be numbers anymore. Notice that. So I evaluate it from 3 to x. Now, it's kind of weird. It still looks like f of x equals a function of t, right? But we're not done yet. This is the magical step that makes it a function of x. To evaluate a definite integral, I plug in the top, right? So I'm going to plug in a what for t? X. So I get 1/3 x cubed plus 1/2 x squared plus x. And then minus, when I plug in the bottom, I get, let's see, 3 cubed is 27. 27 thirds is 9. Plus 3 squared is 9 times a half is 9 halves plus 3. And you end up with this relatively nice cubic polynomial with a constant now. And let's see, that's going to be 12, 24, 33 halves, something like that. So notice when you integrate, you kind of need that initial condition to find c. We kind of have that initial condition. We know that it starts at 3, and that enables us to find our value of c. So we could have done something similar up here. If we had had the equation of little f of t instead of the graph, I could have found the antiderivative of it and come up with, in essence, a formula like this, that now if I wanted to figure out the area from 3 to that x value, it would just be the function value at that moment, okay? Now here's what we're going to do. Once I find the antiderivative from 3 to x, I'm going to turn around and take its derivative. That should be fun. Here we go, big F prime of x. What's another name for big F prime of x? Little f prime of x, right? Same variable. Now using the power rule, we get x squared plus x plus 1 plus 0, taking the derivative of that. Oh, sorry, not f prime. Yeah, just f. If y'all don't speak up and tell me I make a mistake, I usually know I do because there's a lot of squinting out there. Like y'all are really trying hard to give me the benefit of the doubt. You're too kind, very kind. There you go. I apologize. It's what we hope you do on our test. Okay, yeah. Big F prime of x equals f of x. Okay, so the derivative of the antiderivative was x squared plus x plus 1. Have you seen x squared plus x plus 1 somewhere else in this problem? It looks like it's right there, doesn't it? The only difference is in the top, it was a function of t as an integrand. Now it's a function of x. Is it surprising to you that we started with t squared plus t plus 1, we integrated it, picked up a constant, and took the derivative of that and ended up right back where we started? It shouldn't, if you know what the fundamental theorem of calculus is about. Remember, the derivative is essentially a division process, and the integral is essentially a multiplication process, and they are inverses of each other, and so are the integral and the derivative. So we did end up right where we started. So here's what we can claim now. We can claim that the derivative with respect to x of the integral from 3 to x of t squared plus t plus 1 with respect to t is just x squared plus x plus 1. That's what we just proved. The derivative of the integral of the integrand is just the integrand. Start with a number 5, multiply it by 4, divide it by 4. You're back with what you started with, the number 5. We started with t squared plus t plus 1. We integrated it. We took the derivative. We're back where we started. The only difference is it's a function of x instead of function of t. Okay? Will it always be that way? And that's a blanket statement, right? You got to be careful when you agree with that. Well, notice that because this was a constant and that was an x, when I plugged in the x to the top, it became just that function of x, and that's why it is in terms of x. And the constant on the bottom generated a number that when we took the derivative went away, right? So in general, it should work out that the derivative with respect to x of the integral from some constant a to x of some function f of t dt, it should work out to be what? It should work out to be f of x. Yeah. And you can prove that very quickly just by saying the antiderivative of little f is big F, plug in the top minus plug in the bottom and take the derivative. That is right there the FTOC number 2. It's the second part. It basically is the part that says when you take the derivative of an integral from a number to plain old x, you're going to get the plain old integrand, but it's going to become a function of x, not a function of t. Okay? And we state that right here. All right, let's get one problem under our belt before we walk away. Let's do example 9a. It says to evaluate. Now, when you walk up to the problem, it's really important to take inventory. It's asking you for the derivative with respect to x of an integral from 1 to x of secant of t dt. What's important is that you have the derivative of the integral from 1 to x. What should that be? Secant of x. Okay? You don't have to actually evaluate it from the inside out, which is what you'd have to do. You'd have to first find the antiderivative secant, which, do we know that yet? We haven't learned it yet, have we? I don't think so. And then you would evaluate it from 1 to x, and then you would take the derivative of it, and guess what you'd end up with? Secant of x. Okay? The derivative of the integral, they undo each other. They are inverses. Okay? So tomorrow we'll go pretty quickly, and we should be able to possibly finish the notes. There's one big theorem left, the mean value theorem for integrals, but I think you'll have this part down pretty quickly. So the worksheet's out there. Make sure that you're working on it. Don't let it sneak up on you. All right, have a good day.